The electron is one of the most stable particles in the universe. It has existed since the first moments after the Big Bang and will outlast every star in the sky. Its heavier cousin, the muon, survives for about 2 millionths of a second. But there is a third member of this family that almost nobody talks about: the tau. It is nearly 3,500 times heavier than the electron. It belongs to the exact same particle family. It obeys the exact same fundamental rules, and yet it dies in less than 1/3 of a trillionth of a second. That is so fast that even travelling near the speed of light, a tau barely crosses the width of a human hair before it is gone. So what is the tau actually made of? And why does being heavy sentence it to almost instant death? Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, even if you've never thought about it this way. Everything around you, every object you can touch, every surface you can feel, every breath you take, all of it is built from atoms. And every atom has electrons, tiny, almost weightless particles carrying negative electric charge, orbiting the dense nucleus at the atom's core. Electrons are everywhere. They are in your skin, in the air, in the screen you are looking at right now. They hold atoms together in molecules. They flow through wires as electric current. They are responsible for almost every chemical reaction that has ever occurred on Earth, including the ones keeping you alive at this very moment. The electron is one of the most important particles in the entire universe, and it has a remarkable property that sets it apart from most other particles in physics. It is stable, completely, absolutely, permanently stable. An electron that was created in the first moments after the Big Bang, nearly 14 billion years ago, is still here today. It has not decayed. It has not broken apart. It has not transformed into something else. It is the same electron, carrying the same charge, with the same mass, as it had when the universe was less than a second old. That is an extraordinary thing when you think about it. Most particles in nature do not last. Neutrons outside the nucleus decay in about 10 minutes. Muons survive for roughly 2 millionths of a second. Pions last for a few hundredths of a microsecond. The universe is full of particles that appear for an instant and then vanish, transforming into other particles through the fundamental forces of nature. But the electron endures. It sits at the bottom of its family, the lightest of its kind, with nowhere to fall and nothing lighter to become. And that is the key to its permanence. Now, the electron belongs to a specific family of particles in the standard model of particle physics. This family is called the leptons. The word lepton comes from the Greek word leptos, meaning thin or lightweight. It was a reasonable name when physicists first coined it, because the only leptons they knew about at the time were indeed very light. But as we will see, the name turned out to be somewhat misleading, because the heaviest member of this family is not lightweight at all. It is heavier than a proton, heavier than a neutron, heavier than entire atoms of hydrogen. But we will get to that. What defines a lepton is not its mass. What defines a lepton is what it does and does not interact with. In the standard model, there are 4 fundamental forces: gravity, which governs the large-scale structure of the universe; electromagnetism, which governs light, electricity, magnetism, and chemical bonding; the strong nuclear force, which binds quarks together inside protons and neutrons and holds the atomic nucleus together; and the weak nuclear force, which is responsible for certain types of radioactive decay and is the only force that can change one type of fundamental particle into another. Quarks, the particles that make up protons and neutrons, interact with all 4 forces. They feel gravity. They feel electromagnetism because they carry electric charge. They feel the strong force because they carry a property called color charge. And they feel the weak force. Leptons are different. Leptons do not feel the strong nuclear force. They have no color charge. They are invisible to the gluons that bind quarks together. A lepton could pass right through the interior of a proton without the strong force even noticing it was there. This is one of the most important distinctions in particle physics. If a particle feels the strong force, it is a quark or something made of quarks. If it does not feel the strong force, and it is a matter particle rather than a force carrier, it is a lepton. There are 6 leptons in the Standard Model, organized into 3 pairs, which physicists call generations. Each generation contains 1 charged lepton and 1 neutrino. The first generation contains the electron and the electron neutrino. The second generation contains the muon and the muon neutrino. The third generation contains the tau and the tau neutrino. The charged leptons, the electron, the muon, and the tau, all carry the same negative electric charge. They all interact through electromagnetism and the weak force. They all ignore the strong force. In many respects, they are the same particle appearing in 3 different versions, like 3 editions of the same book, with different covers and different page counts, but the same underlying story. The difference between them is mass. The electron has a mass of about 0.511 mega-electron volts. The muon has a mass of about 105.7 mega-electron volts. That makes the muon roughly 207 times heavier than the electron. And then there is the tau. The tau has a mass of about 1,777 mega-electron volts. That is about 17 times heavier than the muon, and about 3,470 times heavier than the electron. This mass hierarchy is one of the great unexplained patterns in particle physics. Why 3 generations? Why these specific masses? Why does each generation weigh so much more than the one before it? The Standard Model does not answer these questions. It accommodates the masses. It allows you to plug them in as parameters, but it does not predict them from any deeper principle. The masses of the charged leptons are among the free parameters of the Standard Model, numbers that must be determined by experiment rather than derived from theory. This is widely considered to be a clue that the Standard Model, as spectacularly successful as it is not the final theory. Something deeper must determine why these numbers are what they are. But before we go further into the mystery of mass, let's talk about the discovery of the tau itself. Because for most of the 20th century, physicists did not even know the tau existed. They knew about the electron. That was discovered in 1897 by J.J. Thomson. They knew about the muon. That was discovered in 1936 in cosmic ray experiments by Carl Anderson and Seth Neddermeyer. And when the muon was found, it was baffling. The physicist Isidor Isaac Rabi reportedly asked, "Who ordered that?" Because nobody had predicted a heavier copy of the electron. It seemed unnecessary. The electron did its job perfectly well. Why would nature create a heavier version of it that served no obvious purpose and decayed almost immediately? That question never got a satisfying answer. And then, decades later, nature did it again. In the early 1970s, a physicist named Martin Lewis Pearl was working at the Stanford Linear Accelerator Center, known as SLAC, in California. SLAC had a powerful new tool, a machine called SPEAR, which stood for Stanford Positron-Electron Asymmetric Rings. SPEAR was a collider. It smashed electrons into their antimatter counterparts, positrons, at high energies. When an electron and a positron collide, they annihilate each other. All their mass and kinetic energy converts into pure energy, which then materializes as new particles according to the rules of quantum field theory. What comes out depends on how much energy was available in the collision. More energy means heavier particles can be created. Pearl and his team were analyzing the debris from these collisions, looking for unusual events, and they found something that did not fit any known particle. They observed events where the collision produced what appeared to be an electron, a muon, and nothing else visible. This was strange. Under the known rules of particle physics, there was no straightforward way to produce an electron and a muon simultaneously from an electron-positron collision without other particles being involved. The simplest explanation was that the collision was creating a new heavy particle and its antiparticle, and each of those new particles was decaying in a different way. One decayed into an electron plus invisible neutrinos. The other decayed into a muon plus invisible neutrinos. The invisible neutrinos would carry away energy and momentum without being detected, which would explain why the electron and muon seem to appear with missing energy. If this interpretation was correct, a third charged lepton had been found, a particle heavier than the muon, belonging to the same family, obeying the same rules, but with a mass large enough that it could decay in ways the muon could not. Pearl announced the discovery in 1975, though the interpretation was debated for a few years afterward. By the late 1970s, the evidence was overwhelming. The tau lepton was real. It was the third charged lepton, the heaviest member of the electrons family, with a mass of about 1,777 mega-electron volts. The name tau comes from the Greek letter tau, which is the first letter of the Greek word triton, meaning third. It was the third charged lepton, and the name stuck. For this discovery, Martin Pearl was awarded the Nobel Prize in Physics in 1995, shared with Frederick Reines, who had detected the neutrino decades earlier. The discovery of the tau was a milestone because it confirmed the three-generation structure of the Standard Model. Quarks also come in 3 generations, and the tau completed the lepton side of that pattern. Now here is something crucial to understand about the tau, and it is directly relevant to the title of our exploration tonight. When we ask what the tau is made of, the answer might surprise you. As far as every experiment ever conducted can determine, the tau is not made of anything. It has no internal structure. It is not built from smaller components the way a proton is built from quarks and gluons. The tau is a fundamental particle, a point-like object with no known substructure. It simply exists as itself, an elementary excitation of the tau field, one of the quantum fields that permeate all of space. This might seem counterintuitive. We are used to the idea that big things are made of smaller things. A mountain is made of rocks. Rocks are made of minerals. Minerals are made of atoms. Atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks and gluons. There is a long chain of composition, each level revealing smaller building blocks. So surely, you might think, the tau, being so heavy, must be made of something. But that is not how fundamental particles work. The tau's mass does not come from internal components. It comes from its interaction with the Higgs field, a field that pervades all of space. We will explore this in detail shortly. For now, the essential point is that asking what the tau is made of is a bit like asking what an electron is made of. The answer, as far as we can tell, is nothing. It is a basic ingredient of reality, rather than a composite assembled from smaller ingredients. Physicists have tested this rigorously. At particle colliders, they have smashed taus and studied how they scatter, how they interact, what comes out when they collide at high energies. If the tau had internal structure, if it were a composite particle made of smaller pieces bound together, those collisions would reveal deviations from the predictions of a point-like particle at sufficiently high energies. The substructure would leave fingerprints, scattering patterns would change, cross-sections would deviate from theoretical calculations. This is exactly how physicists discovered that protons are not fundamental. High-energy electron-proton collisions in the late 1960s and early 1970s at SLAC showed that electrons were bouncing off small, hard objects inside the proton. Those objects turned out to be quarks. The proton's compositeness was revealed by its scattering behavior. The tau shows no such deviations. Every measurement is consistent with the tau being a point particle, a structureless object with no detectable size. Experiments have placed upper limits on any possible internal structure. If the tau has substructure, it must be at an energy scale far beyond what any current accelerator can probe. For all practical and theoretical purposes, the tau is fundamental, and this makes the tau genuinely strange. Because it is a fundamental particle, with the same quantum numbers and the same interaction rules as the electron, yet it is nearly 3,500 times heavier. Imagine two objects that obey exactly the same laws of physics, respond to the same forces in the same way, carry the same electric charge, have the same spin, and yet one of them has thousands of times more mass than the other, without any apparent structural reason for the difference. That is the situation with the electron and the tau. In everyday life, mass differences usually come from differences in composition. A bowling ball is heavier than a tennis ball because it contains more material, denser material, arranged differently. But the tau and the electron are both structureless. Neither contains more stuff than the other. The mass difference comes entirely from the strength of each particle's coupling to the Higgs field, a coupling that the standard model treats as an input rather than something it can explain. This mass difference is not just a numerical curiosity, it has profound physical consequences. It is, in fact, the reason we are here tonight. Because it is the tau's enormous mass that makes it so catastrophically unstable. The mass is what kills it. And to understand why, we need to understand something about how the universe decides which particles are allowed to survive and which must die. In particle physics, stability is not about strength or durability or robustness. Stability is about options. A particle is stable if there is nothing lighter it could transform into while obeying all the conservation laws of nature. A particle is unstable if lighter particles exist that it could become, and if there is a force available to mediate the transformation. The electron is stable because it is the lightest charged lepton. It cannot decay into anything lighter while conserving electric charge and energy. There is simply nowhere for it to go. It is stuck at the bottom of the energy ladder. The muon is unstable because the electron exists below it. The muon is heavier than the electron, and the weak force provides a mechanism for the muon to transform into an electron along with neutrinos that carry away the excess energy. The muon has one meaningful place to go, one primary channel through which it can decay, and so it does. Its lifetime is about 2.2 microseconds. By particle physics standards, that is relatively long. Long enough that muons created in cosmic ray collisions high in the atmosphere can travel significant distances before decaying. The tau is in a different situation entirely. It is not just a little heavier than the muon, it is 17 times heavier. And that enormous mass opens up an extraordinary number of doors through which it can exit existence. The tau does not have one way to decay. It does not have two or three. It has dozens of distinct decay channels available to it. It can decay into an electron. It can decay into a muon. It can decay into combinations involving pions, the lightest particles made of quarks. It can produce kaons. It can produce multiple pions at once. The energy budget is so large that the tau has access to a vast menu of possible final states. And here is the critical principle. The more ways a particle can decay, the faster it decays. Each available channel contributes to the overall decay rate. The total decay rate is the sum of all the individual partial rates. More channels means a higher total rate, and a higher total rate means a shorter lifetime. The tau has so many ways to die that it barely exists at all. This is the central paradox of the tau. It is a fundamental particle. It is not composite. It does not contain smaller parts that can fly apart. It is not fragile in any structural sense. It is a structureless point, as elementary as anything in physics. And yet it vanishes from existence in less than 1/3 of a trillionth of a second. Not because it falls apart, but because the laws of physics give it so many possible transformations that one of them happens almost immediately. The electron, the muon, and the tau are three versions of the same fundamental entity, three excitations of three related quantum fields, obeying the same rules, carrying the same charge, with the same spin. But the difference in mass creates a staggering difference in fate. The electron lives forever, the muon lives for a couple of microseconds. The tau lives for about 290 femtoseconds, where a femtosecond is 1/400,000th of a second. In that time, even travelling at nearly the speed of light, a tau crosses a distance less than 1/10 of a millimetre. It barely makes it across the width of a human hair before it is gone. Same family, same rules, same fundamental nature, but wildly different lifetimes, separated by factors of millions and billions, all because of mass. The tau's weight is its death sentence, not because heavy things are inherently fragile, but because heavy things have more options, and in the quantum world, options are obligations. If a particle can decay, it will. and if it can decay in dozens of different ways, it will do so almost instantly. This is what makes the tau such a fascinating object of study. It is a window into some of the deepest questions in particle physics. Why do 3 generations of leptons exist? Why do their masses follow such an extreme hierarchy? What determines the strength of each particle's coupling to the Higgs field? Is the tau truly fundamental, or does its enormous mass hint at some deeper structure that our experiments have not yet revealed? And there is something almost poetic about the tau's situation. It is made of nothing at all, as elementary as anything in nature, and yet that simplicity does not save it. The universe does not care how fundamental you are. What matters is your mass, the forces available to you, and the particles that are lighter than you. If the menu of decay products is long enough, your existence will be brief. The tau is the heaviest fundamental particle that carries electric charge in the Standard Model, and it pays for that distinction with the shortest lifetime of any charged lepton by an enormous margin. To understand exactly how the tau dies, we need to go deeper into 2 things. First, we need to understand where the tau's mass actually comes from, given that it has no internal structure to account for it. And second, we need to understand the weak nuclear force, the only force in nature that can transform one type of particle into another, and the executioner responsible for every tau decay that has ever occurred. The tau sits at an intersection of deep mysteries. It connects the question of mass, which leads us to the Higgs field, and the unsolved puzzle of why different particles couple to it so differently. It connects the question of generations, which leads us to one of the biggest open problems in particle physics. And it connects the question of stability, which leads us to the weak force and the fundamental rules governing which particles survive and which do not. The electron is stable and eternal. The muon is fleeting but measurable. The tau is gone almost before it arrives, a ghost particle that exists just long enough to leave traces in our detectors before vanishing into a spray of lighter debris. And yet all 3 are the same kind of thing. All 3 are charged leptons. All 3 are fundamental. All 3 obey the same equations. The only difference is mass, and that difference changes everything. So the tau has no internal structure. It is not assembled from smaller components. It is not a bag of quarks like the proton. It is not a bound state of anything. It is fundamental, irreducible, elementary, and yet it carries a mass of 1,777 mega-electron volts. That is more than the proton, which weighs about 938 mega-electron volts. Think about that for a moment. The proton is a composite object. It contains 2 up quarks, 1 down quark, a seething cloud of gluons, and a constant froth of virtual quark-antiquark pairs popping in and out of existence. The proton has structure. It has internal dynamics. It has a complex interior life of strong force interactions that generate the vast majority of its mass through the energy of those interactions. The proton earns its mass through complexity. The tau has none of that. No quarks inside, no gluons, no binding energy, no internal motion. It is a structureless point, simpler than almost anything else in the particle zoo, and yet it weighs nearly twice as much as the proton. Where does all that mass come from? The answer involves one of the most important ideas in modern physics, and one of the most dramatic confirmations in the history of science. The answer is the Higgs field. To understand the Higgs field, you need to first understand something about how modern physics describes reality at the deepest level. In the Standard Model, the fundamental entities are not particles, they are fields. A field is something that exists everywhere in space, at every point, at every moment. It has a value at every location, like temperature has a value at every point in a room. In the Standard Model, there is an electron field that permeates all of space. There is a muon field. There is a tau field. There is a photon field, a quark field for each type of quark, a gluon field, and so on. Every fundamental particle corresponds to a field, and what we call a particle is really a localized excitation of that field, a ripple, a disturbance. When we say there is an electron somewhere, we mean the electron field has a quantum of excitation at that location. The electron is not a little ball sitting in space. It is a vibration in the electron field, the way a wave is a vibration in the ocean. The ocean is the field, the wave is the particle. This might sound abstract, but it is the most accurate description of nature we have. Quantum field theory, the mathematical framework that describes these fields and their interactions, is the most precisely tested theory in all of science. Its predictions match experiments to more decimal places than any other theory in any branch of human knowledge. Now, most of the fields in the Standard Model have a natural resting state of zero. When nothing is happening, when there are no particles around, the electron field sits at zero. The quark fields sit at zero. The photon field sits at zero. Space is empty, and the fields are calm. Particles appear when something excites these fields above zero, creating ripples that we detect as electrons, quarks, photons, and so on. The Higgs field is different. The Higgs field does not rest at zero. In the vacuum, in completely empty space, with no particles present and nothing happening, the Higgs field has a non-zero value everywhere. It fills all of space with a constant, uniform background value. The Higgs field is always on. It permeates the vacuum itself. You are immersed in it right now. Every point in the room you are sitting in, every point in the atmosphere, every point in interstellar space has a non-zero Higgs field value. This non-zero vacuum value is sometimes called the Higgs vacuum expectation value, and it is about 246 giga-electron volts. This number is one of the fundamental parameters of the Standard Model. It is measured, not derived, and it sets the energy scale for how particles acquire mass. Here is how it works. Different particles interact with the Higgs field with different strengths. This interaction strength is called the Yukawa coupling, named after the Japanese physicist Hideki Yukawa. Each fundamental particle has its own Yukawa coupling constant, a number that describes how strongly it couples to the Higgs field. The stronger the coupling, the more the particle interacts with the background Higgs field as it moves through space, and the more mass it acquires. Think of it this way. Imagine a large room filled uniformly with a thick, invisible syrup. Everything in the room is immersed in this syrup. Now imagine different objects moving through the room. A tiny marble passes through the syrup with almost no resistance. It barely notices the syrup is there. It moves freely, almost as if the room were empty. A larger ball experiences more resistance. It is harder to accelerate, harder to stop, harder to change direction. It behaves as if it has more inertia, more mass. And a massive boulder trying to push through the syrup experiences tremendous resistance. It acts as though it is extremely heavy, even though in an empty room it might not weigh much at all. This analogy is imperfect, because the Higgs field does not literally create friction or drag. Particles moving through the Higgs field do not slow down over time. The Higgs mechanism is not about resistance in the usual sense. It is about inertia. The Higgs field gives particles their inertial mass, their resistance to changes in motion. A particle with a strong Yukawa coupling to the Higgs field is hard to accelerate and hard to stop, not because something is slowing it down, but because its interaction with the Higgs field gives it the property we call mass. The electron has a very small Yukawa coupling to the Higgs field, extremely small. As a result, the electron acquires only a tiny mass, about 0.511 mega-electron volts. The muon has a larger Yukawa coupling, roughly 207 times larger than the electrons, so the muon acquires a mass roughly 207 times larger. And the tau has an even larger Yukawa coupling, about 17 times larger than the muons, and about 3,470 times larger than the electrons. The result is a mass of 1,777 mega-electron volts. The entire mass hierarchy of the charged leptons, the vast difference between the featherweight electron and the heavyweight tau, comes down to the strength of their respective couplings to the Higgs field. That is it. There is no structural difference. There is no compositional difference. The electron, the muon, and the tau are all structureless points. They differ only in how strongly they grip the Higgs field, and that grip determines their mass. This is beautiful in its simplicity, but it is also deeply unsatisfying, because the Standard Model does not explain why these coupling strengths are what they are. The Yukawa couplings are free parameters. They are numbers that physicists measure in experiments and then plug into the equations. The standard model says the electron has a Yukawa coupling of approximately 2.94 times 10 to the negative 6. It says the muon coupling is about 6.09 times 10 to the negative 4. It says the tau coupling is about 1.03 times 10 to the negative 2. But it does not say why. There is no equation in the standard model that predicts these values. There is no principle that relates them to each other. This is one of the biggest open questions in fundamental physics. Why does the Higgs field treat these three particles so differently? Why is the tau's coupling thousands of times stronger than the electrons? What determines the pattern? Is there a deeper theory, something beneath the standard model, that would predict these values from first principles? Many physicists believe the answer is yes. The pattern of masses across all the fundamental particles, not just the leptons but also the quarks, is suggestive. It hints at some underlying structure or symmetry that we have not yet uncovered. The masses span an enormous range, from the nearly massless neutrinos to the extraordinarily heavy top quark, and nobody knows why. This hierarchy problem, as it is sometimes called in a broader sense, is one of the driving motivations behind the search for physics beyond the standard model. But for now, let us focus on what we do know. The tau's mass comes from the Higgs field. It comes from the tau's Yukawa coupling, which is large compared to the other charged leptons. And this mass has consequences, enormous consequences. Because in particle physics, mass is not just a number that tells you how hard something is to push. Mass is energy. Einstein's most famous equation, E equals mc squared, tells you that mass and energy are the same thing expressed in different units. A particle's mass is equivalent to a specific amount of energy, and that energy is like a budget. It determines what the particle can afford to do when it decays. When a particle decays through the weak force, it transforms into lighter particles. The total energy must be conserved. The mass energy of the original particle must equal the total energy of the decay products, including their masses and their kinetic energies. This means a decaying particle can only produce decay products whose combined mass is less than or equal to the original particle's mass. If the decay products would be too heavy, the decay cannot happen. There is not enough energy to create them. This is why the electron is stable. The electron's mass-energy budget is about 0.511 mega-electron volts. To decay, it would need to produce at least one lighter charged particle to conserve electric charge, plus neutrinos to conserve other quantum numbers. But there is no charged particle lighter than the electron. There is nowhere to go. The budget is too small for any transaction. The electron cannot decay because there is nothing it can afford to become. The muon has a larger budget. At 105.7 mega-electron volts, it can afford to create an electron, which costs only 0.511 mega-electron volts of mass, plus neutrinos that are nearly massless. That leaves a huge surplus of energy, which goes into the kinetic energies of the decay products. But critically, the muon's budget, while large enough to produce an electron and neutrinos, is not large enough to produce anything made of quarks. The lightest quark-containing particles, the pions, have masses of about 135 to 140 mega-electron volts. The muon, at 105.7 mega-electron volts, simply cannot afford them. So the muon is essentially stuck with one type of decay. It can become an electron plus neutrinos, and that is about it. Now consider the tau. Its mass-energy budget is 1,777 mega-electron volts. This is enormous by the standards of particle physics. The tau can afford to produce electrons. It can afford to produce muons. It can afford to produce pions, which cost only about 135 to 140 mega-electron volts each. It can afford to produce kaons, which cost about 494 mega-electron volts each. It can produce combinations of multiple pions simultaneously. It can produce a rho meson, which costs about 775 mega-electron volts. The tau's energy budget is so large that dozens upon dozens of different final states are energetically accessible. This is the crucial connection between mass and instability. The tau's mass is not just a number, it is a vast reservoir of energy that can be spent on a huge variety of lighter particles. And every possible way to spend that energy represents a possible decay channel. Let me put this in perspective with a simple comparison. Imagine 3 people walking into a store. The first person has 50 cents in their pocket. They look around, but everything in the store costs at least $1. They cannot buy anything. They leave the store with their 50 cents intact. This is the electron. It cannot decay because nothing on the menu is affordable. The second person has $100. They can buy one specific item. They have essentially one option. This is the muon. It has enough energy to produce an electron and neutrinos, and that is basically its only choice. The third person walks in with $1 million. They can buy almost anything in the store. They can buy one expensive item, or several cheaper items, or a combination. The menu is vast. They have dozens of options. This is the tau. Its energy budget is so large that the menu of possible decay products is extensive. And here is the key point from quantum mechanics. In the quantum world, if a particle can decay, it will. The decay happens spontaneously, governed by probabilities calculated from quantum field theory. Each available decay channel has a certain probability per unit time, a certain partial decay rate. The total decay rate is the sum of all these partial rates, and the lifetime of the particle is inversely proportional to the total decay rate. More channels means a higher total decay rate. A higher total decay rate means a shorter lifetime. The tau, with its enormous mass and its vast menu of available decays, has an extremely high total decay rate, and therefore it has an extremely short lifetime. This is why mass determines fate in the world of leptons. The electron lives forever because its mass is too small to afford any decay. The muon lives for a couple of microseconds because its mass affords only one primary decay channel. The tau lives for a fraction of a trillionth of a second because its mass affords dozens of decay channels, and all of them contribute to its rapid demise. Now let us look more closely at just how strange the tau's mass really is, compared to the proton we mentioned earlier. Remember, the proton earns its 938 mega-electron volts through the furious activity of the strong force inside it. But what do the quarks themselves actually weigh? The up quark has a mass of only about 2.2 mega-electron volts. The down quark has a mass of about 4.7 mega-electron volts. Together, the 3 quarks in a proton account for only about 9.4 mega-electron volts. That is roughly 1% of the proton's total mass. The other 99% comes from the energy of the gluon field and the kinetic energy of the quarks, converted to mass through Einstein's equation. The strong force takes a tiny amount of quark mass and amplifies it by a factor of 100 through binding energy and field energy. That is how a composite object builds its mass, through the raw energy of its interior dynamics. The tau has no such interior, no gluons, no binding energy, no strong force dynamics. It is a featureless point, and yet it weighs nearly twice as much as the proton. All of that mass comes purely from its Yukawa coupling to the Higgs field. The tau's mass is entirely a Higgs effect. Every single mega-electron volt of its 1777 mega-electron volt mass is generated by its interaction with the Higgs vacuum. This makes the tau the heaviest known fundamental particle that carries electric charge. The top quark is heavier, at about 173,000 mega-electron volts. But the top quark is a quark. It carries color charge and participates in the strong force. Among the particles that do not feel the strong force, among the leptons, the tau is the heavyweight champion. It holds more Higgs-generated mass than any other lepton by a wide margin. Physicists have spent decades testing whether this picture is really correct. Is the tau truly fundamental? Could its large mass be a sign that it is actually composite, made of smaller pieces that we have not yet been able to resolve? This is not a frivolous question. History has shown that particles once thought to be fundamental can turn out to be composite. The proton was once considered elementary. So was the neutron. So were the pions. All of them turned out to have internal structure made of quarks. Could the tau be next? The way to test this is through scattering experiments and precision measurements. If the tau has internal structure, that structure would reveal itself at high enough energies. When you collide particles at energies much higher than the binding energy holding a composite particle together, the composites behave differently from fundamental particles. Their scattering cross-sections deviate from theoretical predictions. They produce unexpected patterns in the angular distribution of debris. Their form factors, mathematical functions describing how they respond to probes, develop bumps and features that a point particle would not show. Experiments at the Large Electron-Positron Collider at CERN, at SLAC, at the B factories at KEK in Japan and at SLAC, and more recently at the Large Hadron Collider, have all studied the tau with increasing precision. They have measured its properties from its mass to its lifetime, to its decay branching ratios, to its magnetic moment, to its scattering behavior. And every single measurement is consistent with the tau being a fundamental point particle with no substructure. There is no evidence whatsoever that the tau is composite. This does not prove the tau is truly fundamental, of course. It might have structure at energy scales far beyond what our current accelerators can reach. But as far as the data shows, the tau is elementary. Its mass comes from the Higgs field, period. There is no evidence for any other source. This brings us back to the deep puzzle of why 3 generations exist. The standard model contains 3 generations of matter. The first generation contains the up quark, the down quark, the electron, and the electron neutrino. These are the particles that make up ordinary matter. Protons and neutrons are made of up and down quarks. Atoms are made of protons, neutrons, and electrons. The second generation contains the charm quark, the strange quark, the muon, and the muon neutrino. These particles are heavier copies of the first generation. The third generation contains the top quark, the bottom quark, the tau, and the tau neutrino. These are even heavier copies, even less relevant to ordinary matter, even more fleeting. Why does nature repeat itself 3 times? This is one of the most profound, unanswered questions in particle physics. Nobody knows why there are 3 generations. The standard model does not explain it. The number 3 is simply an observed fact. Experiments have confirmed that there are exactly 3 generations of light neutrinos, based on precision measurements of the Z boson at CERN in the early 1990s. The Z boson is a heavy particle that mediates the weak force, and it can decay into neutrino-antineutrino pairs. The more types of light neutrinos that exist, the faster the Z boson decays, and the shorter its lifetime. The measured lifetime of the Z boson is consistent with exactly 3 types of light neutrinos. Not 2, not 4, 3. This tells us there are exactly 3 generations, at least as far as light neutrinos are concerned. But knowing there are 3 generations and understanding why there are 3 generations are very different things. Some theories beyond the standard model attempt to explain the generation structure. Grand unified theories, supersymmetric models, string theory compactifications, and various other frameworks have proposed mechanisms that could produce 3 generations of matter with hierarchical masses. But none of these theories has been confirmed. None has made a prediction about the generation structure that has been tested and verified. The 3-generation pattern remains an empirical fact without a theoretical explanation. What about the mass hierarchy within the charged leptons? Why does each generation weigh so much more than the previous one? The electron to muon mass ratio is about 1 to 207. The muon to tau mass ratio is about 1 to 16.8. These are large jumps, but they do not follow an obvious mathematical pattern. There is no simple formula like each generation is 100 times heavier than the last. The ratios are different between the first and second generation versus the second and third generation, and the mass ratios for quarks follow yet a different pattern. The up quark to charm quark ratio is very different from the charm quark to top quark ratio. The mass hierarchies exist, they are steep, but they are not uniform. Some theorists have proposed that the Yukawa couplings might be generated dynamically by some new interaction or symmetry breaking at a higher energy scale. Other theorists have explored radiative mass generation, where the first-generation masses are generated by quantum corrections from the heavier generations, producing a natural hierarchy. Still others have proposed that the Yukawa couplings are related to the geometry of extra dimensions, with different generations of particles localized at different positions in the extra dimensions, and their overlap with the Higgs field determining their coupling strength and hence their mass. These are all interesting ideas. Some are mathematically elegant, some make testable predictions, but none has been confirmed. The origin of the mass hierarchy remains one of the great open problems in fundamental physics, and the tau, sitting at the top of the charged lepton mass hierarchy, is one of the most dramatic manifestations of this unsolved puzzle. Its mass is a data point begging for an explanation. 1,777 mega-electron volts of Higgs-generated mass in a particle with no known substructure, no compositeness, no complexity to account for its weight. There is one more aspect of the tau's mass that is important for understanding what comes next. In particle physics, there is a deep relationship between mass and the probability of decay. The heavier a lepton is, the more phase space it has available for its decay products. Phase space is a technical term that refers to the range of possible momenta and energies the decay products can carry away. When a particle has a large mass and decays into much lighter products, the decay products can carry a wide range of energies and fly off in many different directions. This large phase space enhances the decay rate. For charged lepton decays mediated by the weak force, the decay rate scales approximately as the fifth power of the decaying particle's mass. This is an extraordinary scaling. If you double the mass, the decay rate increases by a factor of 2 to the fifth power, which is 32. If you increase the mass by a factor of 10, the decay rate increases by a factor of 100,000. The fifth power scaling comes from the detailed quantum mechanical calculation of weak decay amplitudes and the integration over the available phase space. It is not just a rough estimate, it is a precise result from the standard model. This fifth power scaling is the mathematical reason the tau's lifetime is so much shorter than the muons. The tau is about 16.8 times heavier than the muon. 16.8 raised to the fifth power is approximately 1.4 million. So the tau's decay rate due to purely leptonic decays alone should be roughly 1,000,000 times higher than the muons, even before you account for the additional hadronic decay channels that the tau can access, but the muon cannot. When you add in the hadronic channels, the tau's total decay rate becomes even larger. The leptonic channels, where the tau decays into an electron or muon plus neutrinos, account for only about 35% of all tau decays. The remaining 65% goes into hadronic channels, where the tau decays into combinations of pions, kaons, and other light quark-containing particles plus a tau neutrino. These hadronic channels are only available because the tau is heavy enough to produce them. They are a direct consequence of the tau's enormous mass budget, and they roughly triple the tau's total decay rate compared to what it would be with leptonic channels alone. So the tau's mass does two things. First, it enhances each individual decay rate through the fifth power scaling. Second, it opens up an entire category of hadronic decays that lighter leptons cannot access. Both effects push the tau's lifetime down, way down to about 290 femtoseconds, a number so small it challenges our ability to imagine it. The tau's mass is a gift and a curse. It is a gift to physicists because it makes the tau a rich laboratory for studying weak interactions, testing lepton universality, and probing the boundary between leptonic and hadronic physics. The tau is the only lepton heavy enough to decay into hadrons, which gives it a unique role in particle physics. But the mass is also a curse, in the sense that it gives the tau almost no time to exist. It is born and dies in the span of less than a trillionth of a second, leaving behind only a brief spray of lighter particles as evidence that it was ever there at all. The Higgs field gives the tau its mass. That mass gives the tau an enormous energy budget. That energy budget opens the door to dozens of decay channels, and those decay channels, collectively, ensure that the tau's existence is measured in femtoseconds rather than microseconds, or seconds, or years. The Higgs field, in a very real sense, is what kills the tau, not by exerting a force on it, not by destabilizing it, but by giving it so much mass that the weak force has an overwhelming number of ways to transform it into lighter particles. The Higgs field sets the tau up, the weak force knocks it down, and the whole process is over before a beam of light could travel the length of a single grain of table salt. Now we need to understand that executioner in detail. We need to understand the weak nuclear force, the strange and subtle interaction that is uniquely responsible for every tau decay that has ever occurred, and the only force in nature that can change one type of fundamental particle into another. Because the tau does not just fall apart. It does not simply disintegrate. It undergoes a specific quantum mechanical process, mediated by a specific force, involving specific intermediate particles, following specific rules. And those rules explain not just why the tau decays, but exactly how it decays, what it produces, and why the products take the specific forms they do. Every force in nature has a job. Gravity pulls massive objects toward each other. Electromagnetism binds electrons to nuclei and governs the behavior of light. The strong nuclear force locks quarks together inside protons and neutrons with such ferocity that no experiment has ever pried a single quark free. These three forces build things. They assemble matter into structures. They hold the universe together at every scale, from the atomic nucleus to the galaxy cluster. But the fourth force is different. The weak nuclear force does not hold anything together. It does not bind. It does not attract. It does not create structures or maintain stability. The weak force transforms. It is the only force in the universe that can reach into a fundamental particle and change its identity, turning one type of particle into another. And it is the force that kills the tau. To understand how the tau decays, you need to understand what makes the weak force so unusual and why it operates so differently from the other three forces. Every force in the Standard Model is carried by specific particles called gauge bosons. The electromagnetic force is carried by photons. The strong force is carried by gluons. The weak force is carried by three particles called the W+ boson, the W- boson, and the Z boson. The photon, which carries electromagnetism, is massless. This is why electromagnetism has infinite range. The gluons, which carry the strong force, are also massless, but the strong force behaves very differently from electromagnetism because gluons carry color charge themselves, unlike photons, which carry no electric charge. Gluons interact with each other, creating a force that actually gets stronger as quarks move farther apart. This is why quarks are permanently confined inside protons and neutrons. The W and Z bosons, which carry the weak force, are massive. Extremely massive. The W boson has a mass of about 80,400 megaelectron volts. The Z boson is even heavier, at about 91,200 megaelectron volts. These are among the heaviest fundamental particles known. This enormous mass is the reason the weak force is weak. In quantum field theory, forces are transmitted by the exchange of virtual gauge bosons. When two particles interact, they exchange a virtual boson that carries momentum and energy between them. The range and strength of the force depend on the mass of the exchanged boson. A massless boson like the photon can be exchanged over infinite distances, giving electromagnetism its infinite range. But a massive boson like the W or Z can only be exchanged over extremely short distances because creating a massive virtual particle requires borrowing a large amount of energy from the vacuum, and the uncertainty principle limits how long that energy can be borrowed, and therefore how far the virtual particle can travel before it must be reabsorbed. The range of the weak force is approximately 10 to the negative 18 meters. That is about 1,000th the diameter of a proton. It is an absurdly short distance. The weak force operates only within a volume smaller than the interior of a single nucleon. Beyond that range, it is effectively zero. This is why the weak force is weak at low energies. it is not inherently feeble. At very high energies, comparable to the mass of the W and Z bosons, the weak force is actually similar in strength to electromagnetism. In fact, at those energies, the electromagnetic and weak forces unify into a single electroweak force. But at the low energies of everyday particle physics, the massive W and Z bosons suppress the force dramatically, making it appear far weaker than electromagnetism or the strong force. Now, here is the critical property that makes the weak force unique among all four forces. The W boson carries electric charge. The W plus has a charge of +1. The W minus has a charge of -1. When a particle emits or absorbs a W boson, the particle's charge changes. And because charge is intimately tied to particle identity in the Standard Model, this means the particle itself changes type. This is what flavor changing means. In particle physics, the different types of quarks and leptons are called flavors. Up and down are quark flavors. Electron, muon, and tau are lepton flavors. The W boson is the only particle in the Standard Model that can change flavor. When a tau emits a W minus boson, the tau, which carries negative charge, transforms into a tau neutrino, which is electrically neutral. The W boson carries away the negative charge. This is the fundamental process underlying every tau decay. No other force can do this. Electromagnetism cannot change a tau into a tau neutrino. The photon is electrically neutral and does not change particle identity. The strong force cannot do it either. Gluons change color charge, but they do not change quark or lepton flavor. Only the W boson, through the charged current weak interaction, can transform one type of lepton into another. This is why the weak force is the executioner. It is the only force with the ability to carry out the sentence that the tau's mass imposes. Let me walk you through exactly how a tau decay happens, step by step. The tau is sitting there, a fundamental particle with a mass of 1,777 megaelectron volts, negative electric charge, and a quantum property called tau lepton number. It interacts with the electromagnetic field through its charge, and it interacts with the weak field through its weak isospin. It does not feel the strong force at all. At some random moment, governed entirely by quantum probability, the tau emits a virtual W minus boson. The instant this happens, the tau transforms into a tau neutrino. The negative charge that the tau carried is now on the W boson. The tau neutrino carries zero electric charge and has an extremely small mass, almost negligible. It flies off in one direction, carrying away some energy and momentum. But the W boson is virtual. It is not a real particle travelling through space. It is a quantum fluctuation, a momentary borrowing of energy allowed by the uncertainty principle. Virtual particles do not need to have the correct mass for a real particle of their type. A real W boson has a mass of 80,400 megaelectron volts, but the tau only has 1,777 megaelectron volts to work with. There is not nearly enough energy to create a real W boson. So the W boson exists only as a virtual intermediary, a mathematical entity in the quantum calculation that transmits the weak interaction from the tau to whatever particles appear on the other side. The virtual W boson then decays, and what it decays into determines the type of tau decay. There are two broad categories. If the virtual W decays into a charged lepton and a neutrino, the result is a leptonic tau decay. If the virtual W decays into a quark-antiquark pair that then forms hadrons, the result is a hadronic tau decay. In a leptonic decay, the virtual W- can produce an electron and an electron antineutrino, or a muon and a muon antineutrino. It cannot produce a tau and a tau antineutrino because that would require more mass energy than the W has available. So there are two leptonic decay channels. The tau decays into a tau neutrino, an electron, and an electron antineutrino, or the tau decays into a tau neutrino, a muon, and a muon antineutrino. In both cases, three particles emerge from the decay: the tau neutrino, a charged lepton, and another neutrino. Two of the three decay products are neutrinos, which are nearly massless and extremely difficult to detect. In a particle detector, only the charged lepton, the electron or muon, is easily visible. The neutrinos escape detection, carrying away energy and momentum that the detector cannot directly measure. These two leptonic channels are relatively simple and clean. Each one accounts for roughly 17 to 18% of all tau decays. Together, the leptonic channels make up about 35% of the total. But the tau can do something the muon cannot. The tau can decay into hadrons. This is where the tau's enormous mass truly sets it apart. Hadrons are particles made of quarks bound together by the strong force. The lightest hadrons are pions. The charged pion, pi plus or pi minus, has a mass of about 139.6 megaelectron volts. The neutral pion, pi 0, has a mass of about 135 megaelectron volts. The muon, at 105.7 megaelectron volts, cannot produce even a single pion. Its mass is below the pion threshold. But the tau, at 1777 megaelectron volts, has more than enough mass to create pions. In fact, it has enough mass to create multiple pions simultaneously, or to create heavier hadrons like kaons and rho mesons. Here is how a hadronic tau decay works. The tau emits a virtual W- boson and becomes a tau neutrino, exactly as before. But now, instead of producing a charged lepton and a neutrino, the virtual W- produces a quark-antiquark pair. Specifically, it produces a down quark and an anti-up quark, or a strange quark and an anti-up quark. These quarks cannot exist in isolation because of quark confinement. The strong force immediately takes over, and the quarks hadronize, forming one or more hadrons. If the virtual W produces a down quark and an anti-up quark, the resulting hadrons are typically pions. If the virtual W produces a strange quark and an anti-up quark, the resulting hadrons include kaons, which contain strange quarks. The most common hadronic tau decay channel is the tau decaying into a tau neutrino and a single charged pion. This accounts for about 10.8% of all tau decays. The next most common is the tau decaying into a tau neutrino and a rho meson, which is a short-lived resonance that immediately decays into a charged pion and a neutral pion. This channel, tau to tau neutrino plus rho, accounts for about 25% of tau decays, making it the single most common decay mode of the tau. There are channels where the tau produces 3 pions and a tau neutrino. There are channels involving kaons. There are channels involving 4 pions, 5 pions, combinations of pions and kaons, and various other hadronic final states. Some of these individual channels are rare, accounting for less than 1% of tau decays. But there are so many of them that collectively the hadronic channels dominate. About 65% of all tau decays are hadronic. Only 35% are leptonic. This is a direct consequence of mass. The tau's mass opens a gateway to the hadronic world that lighter leptons cannot access. Now let me explain why more decay channels means a shorter lifetime, because this is the heart of why the tau dies so fast. In quantum mechanics, the decay of a particle is a probabilistic process. At any given instant, there is a certain probability per unit time that the particle will decay. This probability is called the decay rate, usually denoted by the Greek letter gamma. The lifetime of the particle is the inverse of the decay rate. If the decay rate is high, the lifetime is short. If the decay rate is low, the lifetime is long. The total decay rate is the sum of all the partial decay rates for each individual channel. If a particle has only one decay channel with a partial rate of gamma 1, the total rate is gamma 1, and the lifetime is 1 over gamma 1. If it has two channels with rates gamma 1 and gamma 2, the total rate is gamma 1 plus gamma 2, and the lifetime is 1 over the sum. Each additional channel adds to the total rate and shortens the lifetime. The tau has dozens of distinct decay channels. Each one contributes its own partial rate. Some channels have large partial rates because they involve light, easily produced final states with lots of available phase space. Others have smaller partial rates because they involve heavier or more complex final states. But they all add up. The sum of all these partial rates gives the total decay rate, and the inverse of that total rate gives the tau's lifetime of about 290 femtoseconds. Compare this to the muon. The muon has essentially one decay channel. It decays into an electron and two neutrinos. There is only one significant contribution to its total decay rate. The result is a much longer lifetime of about 2.2 microseconds. The muon's single channel drips slowly. The tau's dozens of channels pour like a river. There is a subtlety here worth mentioning. Not all decay channels contribute equally. Some channels are suppressed because they involve heavier final states that consume more of the available energy, leaving less phase space. Other channels are suppressed because they require a change in quark flavor that involves a small mixing parameter called a Cabibbo angle. Channels involving strange quarks, which produce kaons in the final state, are suppressed relative to channels involving only up and down quarks, because the coupling of the W boson to the strange quark involves the sign of the Cabibbo angle, which is about 0.225. This means strange quark channels contribute less to the total rate than non-strange channels. But even with this suppression, the kaon channels still contribute a few percent to the total decay rate, adding to the sum. Let me now address a question that might be forming in your mind. If the weak force is so weak, how can it kill the tau so fast? The weak force has a tiny range, and its effects are heavily suppressed at low energies because of the massive W and Z bosons. And yet the tau is gone in under 300 femtoseconds. That seems contradictory. How can a weak force produce such a rapid decay? The answer comes back to mass. The decay rate of a lepton through the weak force depends on the mass of the decaying particle raised to the fifth power. This is a brutal scaling. It comes from the quantum mechanical calculation of the decay amplitude, which involves the weak coupling constant, the mass of the W boson in the propagator, and the phase space integral over the final state momenta. When you work through the mathematics, the result is that the partial decay rate for a lepton decaying into lighter leptons and neutrinos is proportional to the fifth power of the decaying lepton's mass, multiplied by the square of the weak coupling constant divided by the mass of the W boson raised to the fourth power with various numerical factors. The fifth power dependence on mass is devastating for the tau. Let me illustrate this with numbers. The muon's mass is about 106 mega-electron volts. The tau's mass is about 1777 mega-electron volts. The ratio is about 16.8. 16.8 raised to the fifth power is approximately 1.4 million. So the tau's leptonic decay rate alone is roughly 1.4 million times faster than the muon's total decay rate. And that is just from the leptonic channels. When you add the hadronic channels, which roughly triple the leptonic rate, the tau decays many millions of times faster than it would if it had only the muon's single decay channel. But the muon's lifetime is 2.2 microseconds, which is 2.2 times 10 to the negative 6 seconds. If the tau's total decay rate is roughly 7 to 8 million times higher than the muon's, accounting for both the fifth power scaling and the additional hadronic channels, the tau's lifetime should be about 2.2 times 10 to the negative 6 divided by roughly 7.5 million, which gives about 2.9 times 10 to the negative 13 seconds. That is 290 femtoseconds, and that is exactly what experiments measure. The theoretical prediction matches the experimental observation beautifully. The tau's lifetime is precisely what the standard model predicts, based on its mass, the weak coupling constant, the W boson mass, and the available decay channels. This agreement is one of the triumphs of the standard model. The tau's lifetime is not a mystery. It is a calculable, predictable quantity that follows directly from the known properties of the weak interaction and the tau's measured mass. The tau dies fast because it is heavy, and the weak decay rate scales as the fifth power of mass. The tau dies fast because it has many channels, and each channel adds to the total rate.
And the tau dies fast because the weak force, despite being called weak, operates efficiently when there is enough mass energy to work with. Let me now describe what a tau decay actually looks like in a particle detector, because this is how physicists actually observe and study these events. Taus are produced in high-energy particle collisions, typically at electron-positron colliders or at the Large Hadron Collider, where they can appear in the decays of heavier particles like Z bosons, Higgs bosons, or W bosons. When a tau is produced, it travels an extremely short distance before decaying. At typical collider energies, a tau might travel a fraction of a millimeter, perhaps a few tenths of a millimeter if it is highly boosted, meaning it is moving at very close to the speed of light. Modern particle detectors have vertex detectors, layers of ultra-precise silicon sensors positioned very close to the collision point, that can resolve distances of tens of micrometers. These detectors can actually see the tiny gap between the point where the tau was created and the point where it decayed. The tau leaves a short track, barely perceptible, before producing a secondary vertex where the decay products emerge. The decay products depend on which channel the tau chose. If it decayed leptonically, the detector sees an electron or muon emerging from the secondary vertex, plus missing energy from the undetected neutrinos. If it decayed hadronically, the detector sees one or more pions or kaons emerging from the secondary vertex, again with missing energy from the tau neutrino that escapes detection. Hadronic tau decays have a distinctive experimental signature. They typically produce 1 or 3 charged particles, mostly pions, sometimes accompanied by neutral pions that decay almost immediately into pairs of photons. The charged particles form a narrow, jet-like cone of tracks, pointing away from the secondary vertex. This narrow cone of 1 or 3 charged hadrons with missing energy is the hallmark of a hadronic tau decay in a particle detector. Identifying tau decays is important for many areas of particle physics. The Higgs boson itself decays into tau-anti-tau pairs, and recognizing those taus in the detector debris was essential for confirming that the Higgs couples to leptons at all. Beyond the Higgs, tau identification matters for searches involving supersymmetric particles, heavy neutral bosons, and other hypothetical objects that would preferentially produce taus because of their large mass. Getting tau identification wrong means missing potential discoveries. There is one more aspect of tau decay that reveals something deep about the structure of the weak force. The weak force violates a symmetry called parity. Parity is the symmetry between left and right. If you look at a physical process in a mirror, parity symmetry says the mirrored process should also be a valid physical process. Electromagnetism respects parity. The strong force respects parity, but the weak force does not. The weak force is left-handed. This is one of the most startling discoveries in the history of physics, made in 1957 by Chien-Shiung Wu and collaborators. They showed that the weak force treats left-handed particles differently from right-handed particles. Specifically, the W boson only couples to left-handed particles and right-handed antiparticles. It completely ignores right-handed particles and left-handed antiparticles in the massless limit. This means when a tau decays, the process is inherently asymmetric between left and right. The tau neutrino produced in the decay is always left-handed, spinning in a specific direction relative to its motion. The decay products carry angular momentum in specific patterns dictated by this left-handedness. By measuring the angular distributions of tau decay products, physicists can test whether the weak force behaves exactly as the standard model predicts, or whether there are deviations that might hint at new forces or interactions. The tau is particularly valuable for these tests because its hadronic decays carry information about the handedness of the weak interaction in ways that purely leptonic decays do not. The pions and kaons produced in hadronic tau decays have specific angular distributions and energy spectra that depend on the detailed structure of the weak interaction vertex. By measuring these distributions with high precision, physicists can probe the weak force at a level of detail that is not accessible through muon decays or nuclear beta decays. This brings us to a principle called lepton universality. Lepton universality is the standard model prediction that the weak force treats all 3 generations of leptons identically, except for differences arising from their different masses.
The W boson couples to the electron, the muon, and the tau with exactly the same strength. The coupling constant is the same for all three. Lepton universality has been tested extensively using tau decays. Physicists compare the rate at which taus decay into electrons versus muons. They compare tau decay rates with muon decay rates after correcting for the mass difference. They look at the ratio of branching fractions for different tau decay channels and check whether these ratios match the standard model predictions to within experimental uncertainty. So far, lepton universality holds. The measurements agree with the standard model predictions to within a fraction of a percent. But physicists keep testing because any violation of lepton universality would be a sign of new physics, a sign that there is some force or interaction beyond the standard model that treats the three generations differently. Some theories beyond the standard model, such as models involving leptoquarks or extended Higgs sectors, predict small violations of lepton universality that might be detectable with more precise measurements. In recent years, there have been tantalizing hints of possible lepton universality violations in B meson decays at the Large Hadron Collider, where measurements seem to show that B mesons preferred to decay into muons over taus or electrons by slightly different amounts than the standard model predicted. These anomalies generated enormous excitement in the particle physics community. If confirmed, they would have been the first definitive evidence of physics beyond the standard model in the lepton sector. However, subsequent measurements with larger datasets have brought many of these results back into agreement with the standard model. The anomalies have shrunk, though they have not entirely disappeared. The situation remains under active investigation, and the tau plays a central role in these studies. The tau is, in many ways, the most complex and informative of the three charged leptons. The electron is stable and simple. The muon decays in one way and tells us about the basic structure of the weak force. But the tau decays in dozens of ways, bridging the gap between the leptonic and hadronic worlds. Its decays test lepton universality, probe the structure of the weak interaction, provide windows into quantum chromodynamics through the hadronic final states, and serve as sensitive probes for new physics. Every tau that is created in a particle collider exists for less than a trillionth of a second before the weak force transforms it. In that unimaginably brief interval, a fundamental particle with no internal structure surrenders its identity. The tau emits a virtual W boson and becomes a tau neutrino. The virtual W materializes into whatever final state particles the available energy and quantum numbers allow. The tau neutrino flies off undetected. The visible decay products, an electron, a muon, or a spray of pions, appear in the detector and are measured. And from those measurements, physicists reconstruct what happened, confirming once again that the standard model's description of the weak force is extraordinarily accurate. The weak force is the only force that changes flavor. The W boson is the only messenger that can turn a tau into a tau neutrino. And the tau's enormous mass ensures that this transformation happens with breathtaking speed, producing a rich variety of final states that serve as one of particle physics' most versatile laboratories. The tau does not die because it is fragile. It does not die because it is composite. It does not die because something inside it breaks apart. It dies because the laws of quantum mechanics and the structure of the weak interaction guarantee that any particle with sufficient mass and available decay channels will transform quickly and inevitably into lighter particles. The tau has the mass. The weak force provides the mechanism, and the result is a lifetime measured in femtoseconds, a blink so brief that even light barely crosses the width of a human hair before the tau is gone. 290 femtoseconds. That is the lifetime of the tau. Written out in full, that is 0.00000000000290 seconds. That is roughly 290 millionths of a billionth of a second. To call this brief is an understatement so vast that the English language does not really have the right word for it. Brief implies something short but perceptible. A camera flash is brief. A blink of an eye is brief. 290 femtoseconds is not brief. It is practically non-existent. It is a sliver of time so thin that the universe barely registers the tau's presence before it is gone. Let me try to give you a sense of what 290 femtoseconds means in physical terms. Light is the fastest thing in the universe. It travels at about 300,000 kilometers per second. In 290 femtoseconds, light travels about 87 micrometers. That is 87 millionths of a meter, roughly the width of a thick human hair. That is how far the fastest thing in the universe can travel during the tau's entire existence. In practice, taus produced at particle colliders travel even less than this because they are not moving at the speed of light. They are moving at some significant fraction of it, but not all of it. A typical tau at a collider might travel a few tenths of a millimeter, maybe less, before decaying. That is the entirety of its journey through the universe. Created in one spot, dead in virtually the same spot. Now compare this to the muon. The muon lives for about 2.2 microseconds. That is 2.2 millionths of a second. In that time, light travels about 660 meters, more than the length of 6 football fields. The muon lives roughly 7.6 million times longer than the tau. If the tau's lifetime were 1 second, the muon's lifetime would be about 88 days. The ratio between their lifetimes is staggering, and it maps directly onto the physics we have been exploring. Where does this factor of 7.6 million come from? It comes from two things working together. The first is the fifth power mass scaling of weak decays. The tau is about 16.8 times heavier than the muon. 16.8 raised to the fifth power gives approximately 1.4 million. So the leptonic decay rate of the tau is about 1.4 million times faster than the muon's total decay rate, purely because of the mass difference. This is already enormous, but there is a second factor. The tau has access to hadronic decay channels that the muon cannot reach. These hadronic channels account for about 65% of the tau's total decays. This effectively multiplies the tau's total decay rate by roughly a factor of 3, compared to what it would be with leptonic channels alone. When you combine the fifth power mass scaling with the additional hadronic channels, you get a total decay rate for the tau that is roughly 5 to 8 million times higher than the muon's. The inverse of that rate gives a lifetime of about 290 femtoseconds, matching the experimental measurement with remarkable precision. This agreement between theory and experiment is one of the quiet triumphs of the Standard Model. There is nothing mysterious about the tau's lifetime. It is not anomalous. It is not unexplained. It follows directly and precisely from the known mass of the tau, the known strength of the weak coupling, the known mass of the W boson, and the known spectrum of available decay channels. You can sit down with a pencil, write out the Feynman diagrams for each decay mode, calculate the partial decay rate for each one using standard quantum field theory techniques, sum all the partial rates, take the inverse, and you get 290 femtoseconds. The calculation has been done many times by many groups, and it matches the experimental result to within the uncertainties. Experiments measure the tau's lifetime by reconstructing the tiny distance it travels between its creation point and its decay point in a particle detector. At electron-positron colliders like the ones at CERN and KEK, taus are produced in pairs when an electron and a positron annihilate at the right energy. The tau and anti-tau fly apart in opposite directions, each travelling a fraction of a millimeter before decaying. Modern silicon vertex detectors can resolve distances of a few tens of micrometers, which is precise enough to measure the tau's flight distance and from that infer its lifetime. The current world average measurement of the tau lifetime is 290.3 plus or minus 0.5 femtoseconds. That is a measurement with a precision of about 0.2%, and it agrees with the Standard Model prediction. The weak force, the mass of the tau, and the available decay channels explain the tau's lifetime completely. But the fact that the Standard Model explains the tau's lifetime so well does not mean the tau has nothing left to teach us. Quite the opposite. Because the tau's decays are so well understood theoretically, they become a powerful tool for searching for physics beyond the Standard Model. The logic is straightforward. If the Standard Model predicts certain decay rates and branching fractions with high precision, then any measured deviation from those predictions would signal the presence of some new interaction, some new particle, some new force that the standard model does not account for. One of the most important things the tau teaches us about is lepton universality, which we explored earlier. The prediction is very specific and very testable. If you measure the tau's branching fraction to electrons and compare it with the branching fraction to muons, and if you correct for the tiny kinematic differences arising from the electron-muon mass difference, the two branching fractions should be equal. Experiments find that they are equal to within about 0.2%. This is important because lepton universality is not guaranteed by any deep symmetry. It is a feature of the standard model, but it could easily be violated by new physics. Many theories beyond the standard model predict small violations. Models with leptoquarks, particles that connect quarks and leptons, can produce lepton universality violations because leptoquarks might couple more strongly to heavier leptons than to lighter ones. Models with extended Higgs sectors, containing additional Higgs bosons beyond the single one in the standard model, can also produce violations because additional Higgs bosons might have different coupling strengths to different generations. Supersymmetric models, which predict a partner particle for every standard model particle, can produce violations through loop-level corrections involving the supersymmetric partners. Some models even predict that the violations would appear differently in hadronic versus leptonic tau decays, giving physicists two independent handles on the same underlying new physics. If any of these new particles exist, they would contribute virtual corrections to tau decay amplitudes, slightly modifying the decay rates and branching fractions. The modifications would be small, probably at the level of a fraction of a percent, but they could be detectable with sufficiently precise measurements. This is why physicists measure tau properties with such obsessive precision. They are not just confirming what they already know, they are searching for cracks in the standard model, tiny deviations that would point towards something new. The tau is also a crucial player in the study of the Higgs boson. The Higgs boson, discovered in 2012 at the Large Hadron Collider, decays into many different particles. One of the key decay channels is the Higgs decaying into a tau-anti-tau pair. This happens about 6.3% of the time, and it was one of the first channels used to demonstrate that the Higgs boson couples to fermions, meaning matter particles like quarks and leptons, and not just to the W and Z bosons. Measuring the rate of Higgs decays to taus tests the Higgs mechanism directly. The standard model predicts that the Higgs boson should couple to each fermion with a strength proportional to that fermion's mass. The heavier the fermion, the stronger its coupling to the Higgs. Since the tau is the heaviest lepton, it has the strongest Higgs coupling among the leptons, and Higgs decays to taus are the most common leptonic Higgs decays. The rate at which the Higgs decays to taus has been measured at both the ATLAS and CMS experiments at the Large Hadron Collider, and the results are consistent with the standard model prediction. The Higgs couples to the tau with about the right strength. But about the right strength is not exactly the right strength. The current experimental uncertainties are still around 10 to 15%. This means there is room for new physics to be hiding in the data. If the Higgs coupling to the tau deviates from the standard model prediction by even a few percent, it could indicate the presence of additional Higgs bosons, new symmetries, or other forms of new physics. Future colliders, including proposed electron-positron Higgs factories, aim to measure the Higgs-tau coupling to better than 1% precision. At that level, even small deviations would become visible. There is another reason the tau matters for the Higgs, and it connects to one of the deepest problems in particle physics. The Yukawa couplings, the numbers that determine how strongly each lepton interacts with the Higgs field, and therefore how much mass it acquires, span over 3 orders of magnitude across the 3 generations. The tau's coupling is roughly 3,500 times larger than the electrons, and about 17 times larger than the muons. That is an enormous variation among 3 particles that are otherwise identical in every qualitative respect. The spread ranges from an almost vanishingly small value for the electron to a modest but significant value for the tau. Why are these numbers what they are? Nobody knows. The standard model does not predict Yukawa couplings, it merely accommodates them. They are free parameters, inserted by hand to match experimental measurements. This is widely regarded as one of the Standard Model's greatest weaknesses. A truly fundamental theory should explain these numbers, not just accept them. The pattern of Yukawa couplings across all 3 generations of quarks and leptons is one of the biggest clues we have about whatever lies beyond the Standard Model. And the tau, sitting at the top of the charged lepton hierarchy with the largest leptonic Yukawa coupling, is one of the most informative data points in this pattern. Some theorists have tried to derive the Yukawa couplings from more fundamental principles. One approach involves flavor symmetries, mathematical symmetries that relate the 3 generations to each other. If the 3 generations of leptons are connected by some hidden symmetry that is broken in a specific pattern, the symmetry-breaking pattern might determine the mass hierarchy. In some models, the first generation mass is suppressed by 2 powers of a small parameter, the second generation mass is suppressed by 1 power, and the third generation mass is unsuppressed. This naturally produces a hierarchy where each generation is much heavier than the previous one. The tau would be the heaviest because it is the least suppressed. Other approaches use extra dimensions. In models with extra spatial dimensions, different generations of particles might be localized at different positions in the extra dimensions. The Higgs field, also localized somewhere in the extra dimensions, overlaps with each generation differently. A generation whose wave function overlaps strongly with the Higgs field gets a large Yukawa coupling and a large mass. A generation with small overlap gets a small Yukawa coupling and a small mass. The tau might have a large mass because it sits close to the Higgs in the extra-dimensional geometry, while the electron sits far away. These ideas are fascinating and mathematically rich, but none has been confirmed. We do not know whether flavor symmetries, extra dimensions, or something else entirely is responsible for the mass hierarchy. The tau's Yukawa coupling remains an unexplained number, a measured constant of nature without a theoretical derivation. There is a question that haunts particle physics and connects directly to the tau's existence. Why are there 3 generations? Not 2, not 4, not 17, exactly 3. Experiments have pinned this number down with certainty, but certainty about what the number is tells us nothing about why it is 3. No symmetry principle demands it. No equation produces it. The Standard Model simply accepts 3 as an input and moves on. 3 is the number that nature chose, and we observe it without understanding it. Could there be a 4th generation? The Z boson measurement rules out a 4th light neutrino, but it does not rule out a 4th generation with a very heavy neutrino, one too heavy for the Z boson to produce. If such a generation existed, the charged lepton would be even heavier than the tau, and it would be even more unstable, decaying even faster. Its lifetime would be measured in attoseconds or less, a particle that exists for so briefly that detecting it would require extraordinary experimental ingenuity. No evidence for a 4th generation has been found. Searches at the Large Hadron Collider have placed lower limits on the masses of hypothetical 4th generation quarks and leptons. These limits are already in the hundreds of giga-electron volts and climbing. If a 4th generation exists, its members must be very heavy and must have properties carefully arranged to avoid conflicting with existing precision measurements. Most physicists consider a simple 4th generation unlikely given the current data, but the possibility has not been definitively excluded, and it remains an active area of theoretical and experimental investigation. The tau also raises a philosophical question about what it means to be fundamental. We call the tau a fundamental particle. We say it has no internal structure, no substructure, no components. But it has a mass of 1,777 mega-electron volts, a specific and seemingly arbitrary number. It has a Yukawa coupling of about 1.03 times 10 to the negative 2, another specific and unexplained number. It belongs to the 3rd generation, a classification whose origin is unknown. It decays in a specific pattern of branching fractions, each precisely calculable, but following from parameters whose values are ultimately unexplained. A truly fundamental entity, you might argue, should be simple. It should be derivable from first principles. Its properties should follow from the structure of the theory, not be inserted as external inputs. By this standard, the the tau is not fully understood. Its existence is accommodated by the standard model, but not explained by it. We know what the tau does, we know how it interacts, we know how it decays and how long it lives. But we do not know why it exists, why it has the mass it has, or why nature chose to create 3 copies of the charged lepton rather than 1. This is not a failure of the standard model, which has passed every experimental test for over 50 years. But describing the data and explaining the data are different things. The standard model describes, a deeper theory would explain. And the tau, with its unexplained mass and its unexplained generational membership, is one of the strongest arguments that a deeper theory must exist. Something beyond the standard model must determine the Yukawa couplings, must explain the 3-generation structure, must account for the vast mass hierarchies between generations. The tau is not just a particle, it is an unsolved problem, a piece of evidence pointing toward whatever comes next in fundamental physics. Let me close by reflecting on what the tau really is and what its existence tells us about the universe. The tau is a fundamental particle. It is a quantum excitation of the tau field, one of the fields that pervade all of space. It carries negative electric charge, like the electron. It has spin 1/2, like the electron. It ignores the strong nuclear force, like the electron. In virtually every qualitative respect, it is the electron's identical twin. Same rules, same interactions, same fundamental nature. The only difference is mass. The tau couples to the Higgs field about 3,470 times more strongly than the electron, and this coupling gives it a mass of 1,777 mega-electron volts. That mass, and nothing else, explains why the tau behaves so differently from the electron. The electron is eternal because it is the lightest charged lepton. It has no decay channels. It cannot become anything lighter while conserving charge and energy. It sits at the bottom of the mass ladder, with no lower rung to step down to. The universe has no mechanism to destroy it, and so it persists, unchanged, from the moment of its creation until the end of time. The muon is fleeting but measurable. Its mass of 106 mega-electron volts gives it one primary decay channel, producing an electron and 2 neutrinos. The combination of fifth-power mass scaling and the tau's many hadronic channels makes the muon's single decay roughly 7 million times slower than the tau's total rate. The muon lives for 2.2 microseconds, long enough to be detected, tracked, and studied in exquisite detail. Long enough for muons created by cosmic rays in the upper atmosphere to reach the ground, a fact that provides one of the most beautiful confirmations of Einstein's special relativity through time dilation. The tau exists in a different regime entirely. Its mass is so large that it can decay into electrons, muons, pions, kaons, rho mesons, and many other combinations of lighter particles. Each available channel contributes to its total decay rate. The fifth-power mass scaling amplifies each channel enormously compared to lighter leptons, and the sum of all these contributions gives a total decay rate so high that the tau survives for only 290 femtoseconds. It crosses less than the width of a human hair, and then it is gone, leaving behind a spray of lighter particles and a set of neutrinos that escape into the void undetected. There is something profound in this pattern. 3 particles, obeying the same fundamental rules, related by the same quantum numbers, differing only in mass, and yet their fates could not be more different. One lives forever, one lives for microseconds, one lives for femtoseconds. From the muon's 2.2 microseconds to the tau's 290 femtoseconds, their lifetimes differ by nearly 7 orders of magnitude, and the electron outlasts them both by an infinite margin, since it never decays at all. And all of it, every bit of it, traces back to mass, to how strongly each particle couples to the Higgs field, to the energy budget that mass provides, to the decay channels that budget opens, to the weak force that mediates every transition, to the fifth power scaling that makes heavy leptons decay catastrophically faster than light ones. The tau is a particle that is fundamental, yet mortal. It is made of nothing, composed of no smaller parts, assembled from no subcomponents. It is as elementary as anything in the universe, and yet its mass, acquired entirely from the Higgs field, ensures that the universe gives it almost no time to exist. The tau does not break apart, it does not disintegrate, it does not shatter, it transforms. The weak force reaches in and changes its identity, converting it into a tau neutrino and a virtual W boson that immediately becomes lighter particles. The transformation is seamless, quantum mechanical, and inevitable. If a particle can decay, quantum mechanics guarantees that it will. The tau can decay in dozens of ways, and so it does, almost the instant it appears. The tau occupies a strange and beautiful place in the architecture of nature. It is the heaviest particle in its family, the most massive charged lepton, carrying more Higgs-derived mass than any other lepton by a wide margin. It is the only lepton heavy enough to decay into hadrons, bridging the gap between the clean leptonic world and the complex hadronic world governed by the strong force. It is a precision laboratory for testing lepton universality, probing the Higgs mechanism and searching for new physics. It is an unsolved puzzle whose mass and generational placement are clues to whatever theory lies beyond the standard model. And it exists for less than a trillionth of a second. Less time than light needs to cross a human hair. Less time than any clock could measure directly. Less time than almost any process in the macroscopic world. The tau flickers into existence and vanishes, leaving behind only tracks in a detector and a set of measured decay products. But from those fleeting traces, physicists have reconstructed an astonishingly detailed picture of what the tau is, how it interacts, and why it dies. Every branching fraction, every angular distribution, every lifetime measurement confirms the standard model's description. The tau is understood, at least in the sense that its behavior follows precisely from the known laws of physics. But the tau is not explained. We know what it does, but not why it exists. We know its mass, but not why that mass has the value it has. We know it belongs to the third generation, but not why 3 generations exist. These unanswered questions are not signs of failure. They are signs that we are not finished. They are invitations to look deeper, to search for the theory that predicts rather than merely accommodates. The tau is simultaneously one of the best understood and most mysterious particles in the standard model, a particle whose behavior is calculated to extraordinary precision from a set of parameters whose origin remains completely unknown. The electron endures because the universe has no mechanism to destroy it. The tau perishes because the universe has every mechanism to transform it. Both are fundamental, both are structureless, both are excitations of quantum fields, but one is light enough to be eternal, and the other is heavy enough to be gone in a femtosecond. Between those two extremes lies one of the deepest lessons in physics. In the quantum world, mass is not just a measure of heaviness, it is a measure of possibility, and the tau, the heaviest charged lepton, carries so much possibility that its existence is over almost before it begins. It lives for 290 femtoseconds, it crosses the width of a hair, and then it is gone. But the questions it leaves behind will occupy physicists for generations to come.